Okay, here's the review for test 3. Number 1, form a polynomial whose zeros in degree are given. Use a leading coefficient of 1, and I have for problem 1 here, zeros 0, -4, 3, and degree 3. Well, I see if I have 3 zeros, then that's going to require at least 3 factors. So if it's going to be degree 3, then that's already telling me they'll all have a multiplicity of 1. So then I could write down something like f of x is equal to a. And if you really want to just like go completely granular with it, you could think of it as x minus 0, x minus -4, and x minus 3. And of course that all simplifies. So x minus 0 is just x minus -4 is going to be x plus 4, and then x minus 3. And they said use a leading coefficient of 1. So then they're just telling us that we can set a equal to 1, and I have f of x is equal to x times x plus 4 times x minus 3. And I'm happy with that. You can leave it in factored form. It's not in the standard form, but the question doesn't actually ask for it in standard form. But if you wanted to multiply it out, it's actually not too bad. You can multiply out the uh, the two binomial factors first. So then you have x squared, and then I have a 4x, I have a -3x and a 4x, and those combine to just give me x, and then 4 times -3 is -12, and then you distribute the x through, and then you have x cubed plus x squared minus 12x. So either one is correct. Of course, if you leave it in factored form, then there's less of a chance of you making a mistake when you're multiplying it out. But if you're used to doing it the way you did it in the homework, then that's fine too. Okay. So either one is correct. The answer key, I think, only has the one way. Okay, form a polynomial, or I'm sorry, for the polynomial, list each real zero and its multiplicity, determine whether the graph crosses or touches the x-axis at each x-intercept. Okay. So I see 2 real zeros. I can go ahead and just kind of use the lines here to make a table. So real 0. So I have, so from this, I have 7. And then from this, I have -5. And if you have any issues with that, you can always just use the zero product property, set it equal to 0, solve for x. Okay. And then each one of those has a multiplicity. It doesn't have to be a table. You can do it some other way, but as long as you're indicating which one's the 0, which one's the multiplicity, that's fine. So the 7 has a multiplicity of 1. So I'm looking at the exponent. So if there's no exponent, it's implied to be 1. And then the -5 has a multiplicity of 3. And then we want to know the x-axis behavior. So if it's odd, it's going to cross. If it's odd, it's going to cross. And that's all that was asked for. Determine the maximum number of turning points of f. So what we need to determine is the degree. So imagine multiplying this out. So then I have -x squared. So this x plus 7 cubed, the highest degree term is going to be the x cubed that we get. And then we have an x squared minus 1, so times x squared. And then there's a bunch of other stuff that I'm going to sweep under the rug. because I just want to figure out what the highest degree term is so we can figure out the degree. So then 2 plus 3 plus 2 is 7. So I have negative x to the 7 plus a bunch of other stuff that we're ignoring. So my degree is n equals 7. And then maximum possible turning points is equal to n minus 1. So I have 7 minus 1 is 6. Okay. Find the power function that the graph of f resembles for large values of the absolute value of x. This is another one where we're going to imagine multiplying this out. So I have a negative x squared times x cubed times x squared plus a bunch of other stuff. And I end up with a negative x to the 7 plus a bunch of other stuff. Now, a power function was requested, so then I write down y equals negative x to the 7, and that's my power function. I just take the leading term. So the power function um, for the end behavior is the leading term. So in other words, it's the term with the highest degree. Okay. I told myself I wasn't going to like go super in depth with this, but this is one thing that I see missed enough in places that I do want to mention. So if we're asking for a function that determines the end behavior, make sure you're giving us the power function. If we're asking you to describe the end behavior and we don't tell you to show us a function or something, then you're using those, like as x goes to infinity, blah, blah, blah. But look at the question and see if it's asking for a power function or an end behavior function. So power function is the same as the end behavior function. So the end behavior function is just the leading term of the polynomial, just written as a separate power function. That's all that means. All right, so all you had to actually do for this problem was this stuff, and then once you got that, you put it up there. Okay. This here is just review. And then the bottom sentence I would say is clarification. Okay, find a polynomial function f of x of least possible degree having the graph shown. Okay, well, I see some stuff there. So I see, well, let's talk about the x-intercepts first. So we have x-intercepts. So I see negative 2, 0, and 3, 0. Okay. And then we have x-axis behavior. So at negative 2, it's crossing. At positive 3, it is touching. Okay. So now there's a real zero associated with these, right? So we have a real zero of -2 and a real zero of 3 for our function. And there's a multiplicity. Now, with the behavior that we're seeing, we see it cross, so then that means the multiplicity should be odd. You can also look at the shape that the graph is taking on near that x-intercept, and that can help you, kind of motivate what the multiplicity might be if you can identify a shape out of that. All right, so since it's touching at 3, then we would say it's even. So then the least multiplicity, so the least odd multiplicity would be 1, the least even multiplicity would be 2. All right. We can see that there's a y-intercept. So they're just giving us another point. They don't necessarily have to give us a y-intercept. They could just give us any other point that's not an x-intercept, and that can help with the next part. Uh, so that's directly telling us that f of 0 is equal to 9 for our final function. Okay, so let's put some of this together. So we can say that f of x, and I need some leading coefficient in front of everything. I'm just going to call it a. And then I have a -2 as a 0, so I'm going to write a factor that has x plus 2. And then we said it was odd multiplicity, and we're going to give it an exponent of 1. So I'll just leave it as is. And then we have a 0 at +3, so then that's x minus 3. And then we said it was an even multiplicity, and we're going to pick the smallest even number we can use, which is, so far so good. Now we also need to take advantage of the fact that f of 0 should be equal to itself. So we're going to compute f of 0 in another way. So I plug in 0 for x. Okay, so we have f of 0 is also equal to 18a. Now, since f of 0 should be equal to itself, we have 18a is equal to 9. So we're talking about this up here and this here. We're setting those equal to each other. So then if we divide both sides by 18, 9 over 18, that reduces to 1/2. Okay, so there's our a. And now we can put all of this together, so we can take this and this. And then we can write f of x is equal to 1/2 times x plus 2 times x minus 3 squared. And if I'm being too lazy to write it up on the line, I would put a box around that, so I know what my final answer is supposed to be. Otherwise, make sure you put it up on the line. Okay. All right, so this one's got a lot going on. Analyze the graph of the given function f as follows. Determine the end behavior. Find the power function that the graph of f resembles for large values of the absolute value of x. Find the x and y intercepts of the graph. Determine whether the graph crosses or touches the x-axis at each x-intercept. determine the maximum number of turning points, and then use the information from all those other parts to draw a complete graph of f by hand, label all intercepts and turning points. Okay. So let's see. The end behavior function. So imagine multiplying that out. So I have negative x squared times x plus a bunch of other stuff. So then that gives me negative x to the 4 plus a bunch of other stuff. So then my power function for part A is going to be y equals negative x to the 4, right? Just that leading term. And I ignored all the rest of them. Find the x and y intercepts. So that's both combined. So for the y-intercept, that's f of 0, and that just gives me 0. So I can go ahead and list 0, 0. And so x-intercept, actually, let's go. So let's identify the 0, the multiplicity, then the x-intercept, then the x-axis behavior. And then we'll write them down where they're supposed to go. So we have real 0. So 0 is a real 0 from this x squared part. And if you get confused about that, just remember you can set this equal to 0 and solve for x using the 0 product property. So at some point you'll set that x squared equal to 0. So if I plug in 0 for x, the output's 0, which means 0 is a 0 of the function. Okay, and it's that's squared. So if this helps in your thinking, you can think about another way of writing the function looks like this. If that helps you get your head around the idea that 0 is a 0 of the function. So we can see that the multiplicity is 2, the x-intercept is 0, 0, and since the multiplicity is 2, it's going to touch. Okay. Next, we have that x minus 1 factor, so then that's going to be 1. And then we have x plus 3, so then that's a negative 3. These both have a multiplicity of 1. Then my x-intercepts are going to be 1, 0, and negative 3, 0. Since the multiplicity is 1, they're going to cross. Okay, so the rest of my intercepts. So I already have 0, 0 for my y-intercept, but it's, it's both. I only need to list it once. All right, so there's part B completed, and we did a bunch of other stuff along the way. So part C. So at 0, 0, it touches. At 1, 0, it crosses. At negative 3, 0, it crosses. Okay, part D, determine the maximum number of turning points. So the maximum turning points is the degree minus 1, and we have the degree is n equals, well, look at your power function. Whatever that degree is, that's the degree of your function as well. So we have 4 minus 1 is 3. Okay, so we can have at most 3 turning points. Okay. Uh, well, we didn't really get any height on anything. Uh, so we could find an additional point on the function. So we could plug in some other number. So this is just additional points. So f of -1. So then that's going to be -1 times -2 times 2. So that's 4. So we have -1, 4. How about +2? So f of 2. So then that's -4 times 1 times 5. So I get -20. Let's see. How about -2? So we have, let's see, so -4, -3, and 1. So then we get a +12. All right, so there's some additional points. We have 2, -20, and -2, 12. Let's see. I think these will all fit. So as far as using the scale goes, if you're using what's already there, I don't mind if you don't number it or label it. If you're changing the scale, I definitely want to know what you're changing it to. All right, let's get some of these points in. So we have 0, 0, 1, 0, -3, 0, and we had some additional points. Let's see, -2, 12. And let's see, -1, +4. And let's see, 2 and -20. And some knowledge about stuff. So we know what the end behavior is supposed to look like. And I would almost say, we can certainly compute more points on this if we want, but we're already getting carried away. So the end behavior looks like that, right? It's a it's a frown shape. So just paying attention from our x-intercepts. So from this one, and we know it's supposed to be crossing at -3, I'm just going to put an arrow going out of there. And then at the positive one, we know it's supposed to be crossing, and I got carried away and put something all the way down there. So it's doing that. Okay. Now I almost want to say that this guy here is probably a mistake. Uh, so that -2. Oh yeah, that was the last one I did, and let's double check that. So -2, -3. No, I think I did that right. Oh, I drew it in the wrong spot. I said +12 and I drew a -12. Well, that's on me. 4, 5, 6, 7, 8, 9. Sorry about that. Now we don't necessarily know where this is supposed to turn around, so it's not necessarily turning around at that 12. It's hard to know. But it's going through here, and then it's going to touch at 0, and then it has to come back around and turn to go back through the x-axis again. So there should be a turning point here. There's a turning point here. And of course, the 0, 0 is a turning point. So that's also a turning point. And then we have our intercepts. So I labeled the 0, 0, 1, 0, and the -3, 0. All right. Use the remainders theorem to find the remainder when f of x is divided by x minus c. So here they're telling me that c is equal to -1. So then the remainder theorem says that if I just plug that into the function, it's going to output whatever the remainder would have been. So then I have -1 to the 4 plus 8 times -1 cubed plus 12 times -1 squared. So I have 1 minus 8 uh, plus 12. So I have 5. That's it. That's the remainder. So use the factors theorem to determine whether x minus c is a factor of f of x. So here I have f of x is this guy, and then we're dividing it by x plus 8, and we're going to use the remainder theorem. So we plug c equals -8 into the function. So f of -8, the output tells us the remainder, and the remainder theorem says that if the remainder is 0, then the x plus 8 is a factor. Okay, and you can use a calculator to evaluate this if you want. I'm just going to do it by hand. Oh, wait a second, that's plus. Okay. So these cancel out. And then let's see. Well, you know what? I'm just going to jump straight into it. Because again, like I said, this you could just do this with the calculator. So so 8 is 2 cubed, and then 2 cubed squared is going to be 2 to the 6th. And then I have 2 cubed, and then the 20 is 4 times 5, so that's 2 squared times 2, so that's minus 5 times 2 to the 5th. The 32 is 2 to the 5th, so I can factor out 2 to the 5th. So then 3 times that remaining 2 is going to be 6 minus 5 minus 1. So then I have 2 to the 5th times 0, so then that's 0. So since it's equal to 0, then x plus 8 is a factor. So we could just say yes, I guess. Yeah, according to the factor theorem. List the potential rational zeros for the polynomial function. Don't actually find the zeros, just list them. So the rational zeros theorem, I'm going to look at this 6 here. I'm going to look at the fact that it's negative doesn't matter. I want the 4, and what I'm going to do is I'm going to break these guys down into any number that you can divide into 6. Okay, same thing with the 4. So 1 goes in, 2 goes in, 4 goes in. And then all I'm doing next is I'm just iterating through. So 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1. So I'm going to go ahead and start my list up here. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay, next I'm taking 1 divided by 2. Okay, that's new. Okay, 2 divided by 2 is just 1. We already wrote 1, so skip. 3 divided by 2, so plus or minus 3 divided by 2. And I write the plus or minus because our guess could be a positive or a negative. Okay, 6 divided by 2. Well, that's just 3. We already did plus or minus 3, so skip. Okay, 4 now. So we're dividing by 4, so plus or minus 1/4. Okay, 2 divided by 4, that's a half again. We already wrote that. 3 divided by 4, so plus or minus 3/4. Okay, and then 6 divided by 4. Well, that reduces to 3/2, and we already wrote that. So that means we're done. So those are it. So I have 1, 2, 3, 4, 5, 6, 7, 8 unique numbers written down, but we're also considering the positive and the negative. So, you know, that's giving us twice as many total guesses. And you could, if you wanted to do a lot of writing, you could list them, you know, like -1, +1, -2, +2, et cetera, et cetera. But we don't need to do that. The plus or minus is fine. Use the rational zeros theorem to find all the real zeros of the polynomial function. Use the zeros to factor f over the real numbers. So rational zeros theorem. So I'm looking at the 15 and I'm looking at the 4 there. So 15 over 4. So 1, 3, 5, 15 all go into 15. 4, 1, 2, and 4 go in there. So then my guesses are going to be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, uh, plus or minus 1, I'm sorry, yeah, 1/2, plus or minus 3/2, plus or minus 5/2, plus or minus 15/2, and then dividing by 4, plus or minus 1/4, plus or minus 3/4, plus or minus 5/4, and plus or minus 15/4. Okay, so these are all guesses. There's so many guesses. Remember that if you're using a graphing calculator, there's kind of a shortcut if you use the y equals menu. Uh, but basically what you want to do is compute, and I don't suggest that you do this many by hand, but you're basically running a search where you're plugging in these values and you're trying to hit a 0. So f of 1 is 4. F of -1 is 0. Oh, hey, I hit it. So now, as far as the real zeros go, I can go ahead and start my list. So I have one of those now. And now I'm going to use synthetic division to find the depressed polynomial. Okay, so now my depressed polynomial is 4x squared minus 17x plus 15. Let's go ahead and just set that equal to 0. And I think I can factor this. So if we use the AC method, and you could use the quadratic formula at this point, it doesn't matter. Quadratic formula, AC method, completing the square. So AC is going to be 4 times 15, so I get 60. My B is equal to -17. So I need something that multiplies to positive 60 and adds to -17. And you can go super systematic. Now, since that's positive, that means that they have the same side. And since they add to something negative, that means they're both negative. And like I said, you could go, -1 times -60 give you 60, but those add to -61. -2 times -30 multiply to positive 60, and they add to -32. -3 times -20, so then I get -23. -4 times -15, those add to -17. -5 times -12. Oh, I'm sorry, that was 19. My goodness. All right, those add to -17. You know, am I out of stuff yet? I guess you know, -6 times -10. If you're a completionist, this is absolutely unnecessary though. All right, and I think it's done. Uh, well, in any case, I have a winner right here. Now you could just stare at the -17 and maybe something will pop out of your mind. And then I do factor by grouping if I do it in this style. So then by the zero product property, I have x equals 3, and then uh, x equals 5/4. Yeah. So there's the rest of my zeros. So it's 3 and 5/4. Now, if I want to factor this, uh, look at your leading coefficient and just grab that. So the leading coefficient was 4. So just put a 4 up front. And then x minus -1. So that's x plus 1, x minus 3, and x minus 5/4. And that's it. Okay, same deal. So rational zeros theorem. So we're looking at the 20 over the 3. So I have 1 times 1 and 2 and 4, 5, 10, and 20. And then 1 and 3. Okay, so here's my list of educated guesses, plus or minus 1. Okay, all of this. And then now divided by 3. We got pretty huge list. So there's a lot of ground to cover. So use a computing machine. I know all of you could do this by hand, but that takes longer. So f of 1. Well, you can just add the coefficients. That's fine. You get -6. F of -1. So I get -42. F of 2. So if you have a graphing calculator, the y equals menu on that is your friend for these. So I'm just plugging in numbers. If I get a hit, I'm going to just write that one down. Okay. So I checked. I went down the whole list and I finally got a hit. F of 4/3 is equal to 0. So now for my real zeros, I can go ahead and put 4/3. Next, I'm going to do synthetic division. Okay. So 15 divided by 3 is 5, times 4 is 20. Okay, and now I have 3x squared plus 0x plus 15. And let's go ahead and set that equal to 0. So I'll not get ahead of myself. All right, so 3x squared plus 15 equals 0. Now, if you factor that, we have 3 times x squared plus 5 equals 0. And if I set the x squared plus 5 equal to 0, then we have x squared is equal to -5, and then you'll end up with x equals plus or minus radical 5i, which, no, that's not real. So then our real zeros is just the 4/3. Now, to factor this, we can already see we're going to want to have a leading coefficient of 3. So then we can write 3 times x minus 4/3. Now, if you multiply that out, that does not give you a degree 3 polynomial. We're missing something, right? It only legitimately only has one real zero, but don't forget we have these two other zeros that are complex. They're still legitimate zeros, they're just not real zeros. But we're not going to write it in terms of i's. What we're going to do is we're going to go back up and say, oh, well, where did that come from? It came from the x squared plus 5. So that's what we refer to as an irreducible quadratic factor. So then that's just a factor of x squared plus 5. Okay, and if you multiply this out, it will give you the original polynomial. So don't forget about those quadratic factors. Okay, use the intermediate value theorem to determine whether the function has a 0 in the given interval. So my interval is from -2 to -1, so compute f of -2. Okay, did I get all my terms in there? I think so. Let's see, so -3 2 to the 5th plus 5 times 2 cubed plus 5 times 2 squared plus 9. All right, I think we've dealt with the signs just fine now. Now, as far as how we handle the rest of this, there's a few ways that we could approach it. We could just multiply everything out and deal with it that way. Um, I like kind of just factoring things out and making the arithmetic easier. However you want to handle it, I don't care. Well, that 9 did not have any 2's, so I'm just leaving them out. So now I don't have to think so hard. So that 2 cubed, that's 8. So that's -24 plus 10 plus 5. So let's see. So that's, how about -9? All right. So f of -2 is -27. f of -1. Okay, let's see. So -3 plus 5 plus 5 plus 9. So I have 16. Okay, so we have f of -2 equals -27. So that's negative. And f of -1 equals 16, which is positive. Have opposite signs. Therefore, okay, sorry. Therefore, there is at least one real zero in -2, -1 by IVT. So it does. Okay, and that's, I wrote out the long answer right there. But the short answer is it does because they have opposite signs. Okay, but the main idea here is that it does. All right. Find the domain of the rational function. Well, all we need to do is take the denominator and set it equal to 0 and solve for x. So we can write it in set builder notation like this. And if we wanted to write it in interval notation, make sure that you're going in the proper increasing order. So -5 happens first. So then I'm not inclusive on anything because we're skipping these guys. Okay. So either one. So there's the set builder version, and just pay attention to what the test is asking for. So if the test says set builder, use the first one. If it says interval notation, use the second one. But I'm not going to be too angry with you, as in, if you have the right answer, but it's not an interval notation or vice versa, as long as everything is legitimately correct, then it's not going to be too bad for you. Okay, find the vertical asymptotes of the rational function. Is it in lowest terms? So h of x is x plus 11, and then I can factor an x out of the bottom. And I don't see anything canceling, so yes. So then the vertical asymptotes you find by just setting the denominator of the simplified, or the version of the function in lowest terms, set that denominator equal to 0. So then I get x equals 0 and x equals 4. Okay, I'll just write it over there. And these are our vertical asymptotes. Use the graph to find the vertical asymptotes of any of the function. Look for the vertical dashed lines so I can see x equals, so that's -2, and I see x equals a +2, and I'm just looking right here. So I see these vertical lines. So x equals -2 and x equals +2 are the vertical asymptotes. Given the equation of the horizontal asymptote, or give the equation of the horizontal asymptote if any of the function. So this is a degree 1 over a degree 3. So then my horizontal asymptote is y equals 0 because the bottom degree is bigger than the top degree. Okay, same question. So now I have a degree 2 over a degree 2. So since the degrees match, I take the coefficients off of the highest degree terms. So the coefficient on the x squared on top is -3. The coefficient on x squared on the bottom is 1. So it's -3 over 1, which reduces to -3. So there's my horizontal asymptote for that. So if the degrees match, then you take the ratio of the coefficients of the highest degree terms in the numerator and in the denominator. Okay, give the equation of the oblique asymptote if it exists. So they kind of just hinted, but we still want to think about this as a degree 3 over a degree 2. So we see that the degree is 1 more. And now this is where we're required to do long division. There's no synthetic for this. So these guys are all fine. So I can see I'm 3, so degree 3, degree 2, degree 1. And then we're dividing it by x squared. And you may need to pause the video here and there. So firstly, I'm going to take this 2x cubed divided by this x squared. And I get 2x. And I write it above the 2x cubed. Then I take the 2x and I multiply it into the x squared plus 6x plus 5. So I get 2x cubed plus 12x squared plus 10x. But I need to subtract that. There's a few ways of handling that. I'm just going to put parentheses around that, so I have to think about the opposite sign. So I'm taking 2x cubed minus 2x cubed, so I get 0. Next, I'm taking 11x squared minus 12x squared, so I get negative x squared. And then 5x minus 10x, so I get negative 5x. Technically, if we're doing this correct, I'm going to bring that -1 down next. And now I'm going to take this negative x squared divided by this x squared. And I get -1. And I put a -1 up here. At this point, as soon as you have whatever, as soon as you have that linear function, you stop. you don't need to complete the long division. We don't care about the remainder here. So my linear function is y equals 2x minus 1, and that's my oblique asymptote. Okay, solve the inequality. So this is a polynomial inequality. And so we have real zero, multiplicity, and then signs. So my real zero, the first one I see is -1. It has a multiplicity of 1, so it's going to have opposite signs. Next, I see a real zero of 3. It has a multiplicity of 1, and that means it's going to have opposite signs. I make a number line. I have -1 and 3, so I have these regions now. Oh, I'm getting ahead of myself. So I put my circles in. I look at the inequality, it's or equal to, so these are closed circles or filled in circles. So then that's -infinity to -1 inclusive, -1 inclusive to +3 inclusive, or 3 to infinity. Okay, inclusive on the 3. And then we need a test value. So we could test -2. And I'm going to refer to this as f of x. So f of -2 is going to be -1 times -5. So I get a +5. So I'm going to mark this region plus. Now, since my multiplicity on the -1 is odd, then they're going to have opposite signs. So then the next region should be negative. The multiplicity on the 3 is also odd. So it's also going to have the opposite sign in the next region. So that's going to be a plus. We were looking for less than or equal to 0. So then we want the negative region. So then my final answer is going to be -1 to 3 inclusive on both. X cubed minus 2x squared minus 3x greater than 0. Well, that's f of x. So we have f of x is x cubed minus 2x squared minus 35x. We can factor out an x, and then we have x times x squared minus 2x minus 35. And I can see that that factors to x minus 7 times x plus 5. So now we can talk about the real zeros, the multiplicities, and the signs. So for just an x as a factor, then the 0 corresponding to that is 0. So you have to be thinking, what do I plug into this factor to make it 0? Well, the factor is just x, and the answer is 0. Okay, and then we have -7. Oh, sorry, not -7. Hold on, my computer's lagging. Did anything important get erased? I don't know. Okay, so for the x minus 7, the thing that makes that factor 0 is 7. And then for the x plus 5, -5. Or you can set that equal to 0 and solve for x. Okay, the multiplicity of each one of those is 1, which means they have opposite signs on each side of that corresponding 0, which is going to make this really easy. So I have -5 0, and 7. And we have greater than 0. It's strict, so it's not inclusive, so I'm going to use open circles. Then we need a test value somewhere. We can pick any region. And speaking of the regions, let's go ahead and label those so we don't get in trouble later. So negative infinity up to -5. So nothing's inclusive, so parentheses, -5 to 0, parentheses, 0 to 7, and then 7 to infinity. And let's just test 1. So test x equals 1. So f of 1, and we have a few ways we could compute that. We could do 1 times -6 times +6, so we get -36. So we can see that that's negative. So negative, and then all of these are going to be opposite signs, so that the region's going to be positive, this region's going to be positive, and then this region's going to be negative. We want greater than 0, so we want the positive regions for our final answer. Okay, so we marked -5, not inclusive, to 0, not inclusive, union with +7, not inclusive, to infinity. Okay, now we have a rational function. So we have x plus 11 times x minus 5 all over x minus 1 greater than or equal to 0. Let's refer to this as f of x. And with a rational function, we want our critical values. So values that are real zeros and values that where the thing is undefined. So up top, those are giving us the zeros. So -11 and +5. Now you have to be careful that those are in the domain. In this case, it's very clear that they are because it's in lowest terms. So real 0, multiplicity, signs. So I have -11, +5. They each have a multiplicity of 1, which means they'll have opposite signs. Next, we want to look where it's undefined. Okay. Pardon my lag. So very similar. So we can see it's undefined when x is equal to +1. That has a multiplicity of 1. So then that means you get those opposite infinities. So same deal. One is going to be in the positive, one's going to be in the negative. Now, let's mark these down. So we have -11, and then we have a 1 and 5. And then, like I said, I like to mark these with circles, and I don't even know why that just happened. So the -11 gets a circle, 1 gets a circle, 5 gets a circle. Now the things that are real zeros, we need to check and see. It says or equal to. So the -11, since it's a real zero, if we plug -11 into the function, then that outputs a value that is defined. If we plug in 1, it's undefined. So we absolutely cannot plug 1 into the function. It's important, though, as a boundary. And then positive 5, we can plug into the function. So the function is fine if we do that. That 5 is in the domain of f of x. Okay, so we've established that. We have these regions, negative infinity up to negative 11, and it would be inclusive on the negative 11. And then negative 11 inclusive up to 1, which would be not inclusive. And then 1 not inclusive to 5 inclusive, and then 5 inclusive to infinity. Okay. And then we need a test value. So let's go with 0. So test x equals 0. So then f of 0 would be 11 times negative 5 over negative 1. So we get a positive 55. So that's greater than 0. So then this region would be positive. All of these are marked as opposite signs. So if we go to the negative 11, then the next region over there is negative. If we go to the positive 1, that also has opposite signs. So since this region is positive, then the next is negative, and then at the 5, that's going to have opposite signs as well. So negative to positive. And then we wanted greater than or equal to 0. So we want the positive regions for our final result. Okay, so then our solutions are in the interval negative 11 inclusive to 1 not inclusive, union with, oops, I made a mistake, so now I have to, okay, there we go. And then 5 inclusive to positive infinity. All right. And that's it. Good luck on the test, everyone.